Right? This is the most important class. Obviously, that's bullshit, right? Your number one job is to survive the next 3 weeks. Okay? So I'm going to crank it up again today. Let's go to the board over there. Okay, let's go to the board over there. So when you look, we're done with step 1. Now we're going to step 2. So what happens here? So remember, you gotta start that rhythm, right? Start that rhythm. When I'm deriving a second order differential equation, we require 2 initial conditions. And the most important initial condition is getting that derivative of time. So that would be the current of the capacitor or the voltage of the inductor. That's the most important one. Okay? Where we get that is in here. This is the reason why we use to define equation variable 1, variable 2, to guide you to get that. And if we do that here, when we get to step 3, it'll be easier for you. So here we go. You focus on the variable that you're solving for. How are we treating this? 2 variables. One for IL and VC, and a second equation, IL, VC. We need those 2 equations. We apply KVL. We start off with 4 variables, or 3, and then we connect these 2. And when we connect these 2, then we do a 3-step process. We rewrite the resistor values in terms of VC and IL. We implement this operator technique, and then we identify that derivative term. Now remember, we saw yesterday that sometimes it's tricky because you'll have 2 equations that have this variable here, and then we're going to have to solve those 2 equations to get it. So it's not totally trivial. So we matrix up the 2 equations, right? That operator, which I think I called the coefficient matrix operator, this is an operator equation. So then we use this Cramer's rule and we get 2 terms, right? So what I do here is if I'm solving for the first variable, I'll take my C's and I put it in my A columns. A11 and A21, just like this. And if I'm solving for 2, then I take this and I put it in the second column, which is the term for that, where the determinant of D is the cross product of these guys right here. So in the end, what do we get? We end up getting a second order differential equation. So the solution of the matrix gives me this equation right here. I typically don't like writing it in operator form. I mean, I prefer operator form than this form, but I just did it for here. Now note, this has very distinct form. I isolate the second order differential equation term, and then I just adjust my constants. So to check this equation right here, I look at x infinity. X infinity tells me that it has to be a constant, so immediately it sets up that term and that term go to 0, but it sets up the equation right here to solve for B. That B is our force response. So we have found one solution by looking at this equation. So then the second thing here is that we got to derive the general response. Because it's a second order equation, there are 2 terms. There's 2 terms for the natural response here. So I identify A1 and A2 as those constants that we got to find here. So to determine the natural response, we got to solve the characteristic equation. We look at this guy. For the natural response here, the solution is 0. Excuse me, or the forcing response is 0. And then I assume a solution of this form. When I do that, then I end up having to solve this quadratic equation. This is what we call the characteristic equation. And then I get the solutions and they look like this. So S1 and S2 are the solutions to this that equation for the homogeneous solution. And then what you find here is that then I get S1 and S2 and I plug them into this. So my job right now is to go figure out what is S1 and what is S2. Okay? So that means we're starting this second step. starting this second step. Now I started all the way at the end and hope that nobody erases it. If it gets erased, I'll rewrite it. And then what am I going to do? I'm going to keep adding to this thing. So there's a lot of detail in there. So what we want to do here, okay, here we go. So now what we want to do here is that we want to, so we're going to determine the natural response. So this implies here that what I'm looking at, that I'm looking at a solution that looks like this. So and alpha is known as the, what do they call it? The Napier, I think it is? Napier frequency. And omega naught is the natural frequency. Just for language. By the way, we can measure these guys in the lab. So what I want to do here is that I want to give you a very brief analogy. And this is what they call a damped oscillator. And what you're seeing here is that when I have a damped oscillator, it turns out that if I have a system where I have a mass on here, if I displace this thing some amplitude A, so where this mass is all the way over here, what we know here is that this mass, if this is the equilibrium point, how about if I write EQ, the equilibrium point? What's going to happen here is that this thing is going to oscillate from this point to that point. And what we do here is that then we apply the net force, and we get minus kx. And when you get minus kx, this guy will then oscillate forever, assuming that there's no friction. However, if there is friction, let's call this B times V, this friction here dampens the motion. Okay, that friction dampens the motion. And when you solve this problem here, so depending on the friction, you can have a solution to this equation. And what you get here is that you get an equation that looks something like this. You'll get mass times acceleration, which is m d2x dt, which is then equal to plus v dx dt plus k x equals to some, let's say, if there's no source here, it's got to be 0. So what I want you to do here is I want you to look at this equation right here. This equation is identical to that equation that we solved for. So this is identical in form to the RLC circuit equation. So if I look at our equation looks like what? Plus and omega naught squared x. So for the natural response, you can see that these two equations, they match up. So that means when I have a circuit, an RLC circuit, for example, if I have a harmonic oscillator, it's going to go through its motions here. So since I wrote on the board, I got to pull down the screen to show you what I have. And what you're going to see here is that what kind of types of oscillations are you going to see here? So what you're seeing here, up above, I have a mass on a spring here. And if I have zero damping, okay, if it's undamped, then this thing will oscillate forever. Right? There's no change in the amplitude, and it continues to just oscillate forever. But there is something that we should look at here, is that if I come in here and I give a little bit of damping, that means there's a little bit of friction here. What you're going to find here is that this guy then starts to oscillate. But the oscillation, you can see, has its amplitude decreasing. So therefore, we call it an underdamped oscillator. So any solution that has any wiggle underneath the equilibrium point is called underdamped. Now what you'll find here is that I could come in here and I could modify this guy. And if I come here, and if I look at this oscillation, you can see that it just barely touches underneath here. So if you were in the circuit, you would be adjusting the resistance just right to almost get it not to do that. But this one's a pretty hard one. But if I go to where this is critically damped, what you're seeing here is that when it's critically damped, this is the fastest way to zero. So if I look at this guy here, it looks like this is taking longer, the blue, but remember this brown one is doing what? There's an oscillation, a very small oscillation. But this guy is the fastest way to do that. And this is critical. And by the way, that's really hard to see in the lab. Because you'd be looking at your oscilloscope screen going like, what do I mean by that? Where is it at? And you're sort of like tweaking things very, very finely. But if I go a little bit higher where I have more damping here, what you'll see here is that you can see that there's a slight difference between the brown and the red, which is really hard to see. But you would think that if I put a lot of damping, it should take what? It should be faster to get to the equilibrium, right? It should just go like this. No, think about it. If I have a lot of damping, the oscillator must be doing what? Moving slowly. So if I increase the damping considerably, you'll see that if I do that, this guy takes longer to move to that. So when you look at the door hinges, and you want to know what closes the door very, very, very quickly because it's a damped oscillator, it's the one that we call critical. So the critical oscillator is the fastest to zero. Why do we care about this? I'll tell you why we care about this. Because this is exactly what happens in a circuit. So if I look at what happens in a circuit, solutions tell me what the oscillations have to do. So if I look at this guy here, what we find here is that now if we apply the harmonic damped oscillator ideas to an RLC circuit, we get the following. And the following is what? I have my solution. You can see what determines everything is what happens in that radical right there. Okay? It depends on what happens on that radical. And what we see here is that there's going to be effectively 3 cases here. Okay, there's going to be 3 cases here. So let's look at case 1. Case 1 that I picked here is what's known as critically damped. So when I look at critically damped, this means here when alpha is equal to omega naught. When alpha is equal to omega naught, what this immediately tells me here is that if I look at S1 and 2, this radical tells me that it's got to be minus alpha plus or minus 0. So there's no solution here. So what you're seeing here is that now what you get here is you get identical real roots to the equation. So the only way you can have that is if, this tells me that the only way you can do that here is that the solution, and as you may remember, says that if I have a critical thing where I have identical real roots, then there's no choice. The solution's real obvious. It says e to the minus alpha t, right? Alpha's the same. So when you look at that solution here, that's one of the solutions has to be that. But the problem is that if I have identical roots, I always have to have what? A linear combination of the constant plus I have to multiply by t. So in other words, if S12 is equal like this, then I have no choice but to have that solution. And when I map this guy, this means here, x critical means that this solution here is the fastest one to 0. And it doesn't cross the time axis. Okay, so when I look at this guy here, does not cross time axis. And if I look at case 2, I'm going to have, I'm going to go to overdamped. And if I look at overdamped, what we're seeing here is that we have alpha greater than omega naught. That's a mistake. It's actually the other way around. And what I have here, so I got to do this here. So if I have overdamped, then this must be true. And so when you look at that solution here, that means I get a positive number in the radical. Right? Overdamped has to be that. When omega naught is smaller than alpha, then I get the complex roots, and that's going to give me underdamped. So I'm correct. So then what this tells me here is that then S12 must be minus alpha plus or minus alpha squared minus omega squared. And I get that root right there. So these are what? What you get here is you get two distinct real roots. And believe it or not, this is one that's a pain in the butt sometimes. And the way I really typically solve this thing is I actually look at the characteristic roots and I say, can I factor them out? And if you can factor them quickly, then you'll do that. And most of the solutions that you'll see with me, if you get overdamped, I'm going to make it so that you can eye it. You can go in there and go like, okay, these are the roots. So once I do that here, then what this tells me here is that there's only one solution. And that one solution for overdamped has to be A1 e to the S1t plus A2 e to the S2t. Now note, each of these roots will be negative. So S1 and S2, or S1 and S2, will always be less than 0. In other words, they're negative. Does that make sense? What would happen if this one of these S1s was positive? As time increases, the exponential solution would go what? To infinity. So if you calculate these things, and I've seen some of you guys, like you'll punch it into your calculator wrong, and you'll end up getting positive S1s, and then you go, no, it goes to infinity. I'm going like, dude, what are you talking about, right? Because you know that these are damped. Nothing can make the oscillations of that spring go to infinity in amplitude. So you got to remember that if you get some funky number, think about it. So then this tells me here that for this scenario right here, I get this solution right here. And so if I look at this guy here, it looks like it's critical, but it's not. Because this takes longer. So if I look at this guy here, this guy takes, let's say it takes longer to get to this point. So once again, so it takes longer to reach 0. And then we're left with the last case here, case 3. And that has to be underdamped. And this is the painful one. So if you get anything from me and it's underdamped here, you're going to really focus here because the roots have to be simple. Otherwise, you get into this, it gets nasty. So underdamped implies that omega naught is greater than alpha. Which then means here you get S12 right away because omega naught is greater. That means when I look at this guy, I'm going to get a negative sign under the radical. Okay? So that means if I do this, this implies here I get a negative sign in the square root term. So now I abbreviated square root. SQ square RT root. So that means this implies here that you get complex numbers. Okay, you get complex numbers. So the way we deal with this thing here is that then we write it like this. We go minus alpha plus or minus j omega naught squared alpha squared. So now this guy gives me a positive number, but now I have this j here. And so what I get here is that I get two distinct roots. Complex roots. for this scenario here. So when I look at my solution here, then what we find here is that the solution should be like this. So underdamped will then be e to the minus alpha t. That's for the first term right here. And then what you get here is that because of these complex numbers, there's a way that you can manipulate it that you get sine and cosine. I want to make sure I write it with my notation, so I always follow that notation. Okay, so I always call A1 the cosine term plus A2 the sine term. Now there's something special about that. So typically what they do here is they put a little d on this guy. Where omega d, we got to distinguish between omega naught is equal to omega naught squared minus alpha squared. So this is the damped frequency. So what do I have? I have this solution right here. I got this guy right here. And I always get that when I choose that guy right there. So typically, when I get these damped scenarios here, this is what we got to do. What we got to do here is that I look at this equation right here. I look at this equation, and I look at 2 alpha, and I look at omega. What I would do here is that I would calculate 2 alpha and omega naught so that I get those two terms. And then I go and I look at these cases here. If I know it's underdamped, you got to bite the bullet. You got to do this whole spiel right here. If you get overdamped, what's nice about overdamped is that the vast majority of the time, you'll see that you'll be able to look at the roots and just say, I can factor this second order equation, right? I can factor this guy so that I can immediately pick out what is S1 and S2. That means that these numbers have to be nice. Now note, sometimes I'm going to make mistakes, of course, right? And to tweak the circuit to get nice numbers on this, it's not easy. But I aim to pick nice numbers. And if I get identical roots here, then this one I think is also very fast because it's really omega, that alpha you're getting, and so that quickly just gives you that term. Let's go apply these things. Okay, let's go apply these. Let's see. How much time do we have? Oh yeah. Let's move through this thing quickly. So what I'm going to do here is that I'm going to look at the example. I'm going to erase the board. And let's see here. Let's see if we can do this within a half an hour. Okay, we're going to move. So what am I going to do with every single example? I'm going to do step 1. Why am I doing step 1? Because you got to do this. Okay? The more practice, the better. And I'm going to use the matrix technique. Here's the
the equation over there is 2 alpha.
Yes.
Why are we using 2 alpha in the when we're finding the quadratic?
Because when I choose 2 alpha and omega naught like this, then the roots look like this. That's the only reason. It gets rid of the 4. And it gets rid of the denominator. That's why. Okay, here I go. I'm going to erase. So I'm not going to give you time to think about it, okay? I'm just going to do that. Why? Because I want to move through these things quickly. So I think the solutions to these things are straightforward. Okay? It's the next step we got to worry about, step 3. You know, I should be spiking my tea in the morning, right? That way, we're more laid back. I mean, what's the canister, right? All those hard liquids are clear, right? Okay, here we go. You know what, I'd probably say no thank you. Some of those water bottles, Peter washed them out. They're pretty nasty. Okay, here we go. So look, I'm going to start with this circuit. There's a solution to that, but I'm going to move through these quickly. Let's see if we can do these three, let's say 10 minutes each. Okay, ready? Here we go. So I'm going to go right down the line. I'm going to start with example right here. Okay, so here's my circuit. So if I have nice numbers for these values here, let me tell you, that typically means nasty roots. Okay? I mean, it's hard to get clean roots, but here we go. We want to get the current of the inductor. Okay? Here we go. Let's derive it quickly. Okay? Let's derive it quickly. So what am I doing? I'm going to get that current. How do I get that current? I'm going to use KCL, KVL. So what variable am I looking for at the end? Equation 2 is the derivative of that inductor right there. Here we go. I'm going to use the matrix form. So I'm going to apply KCL first. What does KCL tell me? I have the source coming in, and then look at the currents. They split right there. So I get the current of 1 ohm plus the current of the inductor. What is my job? I got to get the current of the 1 ohm. How do I know the current of the 1 ohm? Note that this 1 ohm is parallel to these. So this tells me here that the 1 ohm must be the voltage of the inductor, the voltage of the capacitor divided by 1 plus IL. Okay, so what am I going to do next? I'm going to convert VL, excuse me. So I'm going to get what? I'm going to get L, which is 2. Then I get S hat IL plus IL plus VC equals I source. That's my first equation. Let's go to the second one now. KVL. I have to relate these two together here. And look at, we already did that in essence. What I'm going to do here is that I'm going to use a KVL around this loop here. So the voltage of the cross to 1 ohm must be, oh man, there's a lot of ways I can do this. The voltage of the 1 ohm has to be what? Equal to the voltage of the inductor plus the voltage of the capacitor. So how do I get the voltage of the inductor? Note, I already used this loop here. So if I do that, I could run it to be redundant. If I look at this node, here, you can see here that I source must be IL plus I1. Right? I'm looking at this node, I'm looking at KCL right there. Current coming in, it gets split between the two. So I'm going to plug this guy right into here now. Okay? So what's this guy here? So I get the voltage of 1 times the current of this guy, which will be I source minus IL, equals this guy here, which has to be 2S hat IL plus VC. So look at that. I got everything in terms of VC and IL. So then this tells me here that I get the equation here. Look at that IL. I'm going to bring it to the other side. So I'm going to get 2S hat IL plus IL plus VC equals to I source. I'm getting the exact same solution. Did I mess up here? Yes.
Yeah, you use this.
Can you do something else besides I source equals IL plus I1? Because that's your original equation for KCL.
This one I use KVL. This one here I use KCL.
Do this series transformation, would that make it easier?
Say that again?
If you did a source transformation, would that make it easier? Because you have one loop, and an IL would equal IC.
Sure, you could do that. But the question is, yes,
IL equals IC anyway, so don't you have two equations?
oh,
One,
you know what? You should take my pen and I should sit down. Did you hear what he said? He just says, these guys are the same. There you go. So, look what I'm going to do here. This is the same as that one, right? So it's the same thing. Since I can do this and you can't do this, I'm going to do it. So this tells me here that IL has to equal IC. Which then tells me that IL, look at the IC, I'm going to bring it to the other side. It's going to be minus C, which is 1/2 S hat BC equal to 0. Thank you for the help. So that being the case, I'm going to matrix this guy up. If I matrix this guy up here, I'm going to, so the first thing, I'm solving for the inductor current. So that means this guy tells me I got to look for the derivative of the inductor current. Right? Because that's what differential equations do. Look at that, this guy's right here. So this is my equation 2 here. This is the one that has the variable S hat IL. So now I'm going to matrix this guy. So if I look at that, I'm going to write IL minus 1/2 S hat VC equals to 0. Then I'm going to get 1 plus IL, excuse me, so I get IL times 1 plus 2 S hat plus VC equals I source. So if I write a matrix for this thing, then it should be 1 plus 2 S hat, then I'm going to get minus 1/2 S hat, and then I'm going to get 1 IL VC equals 0 I source. Could I have written this equation first and then that one second? Yes. So now I want the solution to this guy. So the solution to IL, look at it, it's the first one, it's not the second one. Right, it's the first one. So if I look at the first one here, that means solution to IL looks like this. So it's got to be B IL equals what? Since this is the first one, I take this column and I replace it with the first column, which is associated with the IL. So then I write 0 I source minus 1/2 S at, and then 1. Right? So you can see here, remember, that's, so if I go like this, I get a positive. If I go backwards, I get a negative. So here I go. To get the determinant, I get 0 times 1, 0, and then I take this guy here. So this will be 0 minus 1/2 S hat operating on S source. So that in the end, this is equal to 1/2 S hat I source. So now I got to calculate D. So D is this matrix right here. That's D right there. So if I do that, I got to take the determinant of that. So remember, this is positive, that's negative. So if I look at D, it's got to be 1 minus plus times 1 times 2 S hat. Okay, right there is D. That's my operator matrix, giving me that solution. So then this is 1/2 S hat IS. So now I just got to clean it up. So if I clean this guy up here, I got to multiply through. So that minus and minus is a positive. So I'm going to get 1. My first term gives me 1/2 S hat. My second term gives me S hat squared. And there's my equation right there. So what am I going to do? I'm going to go get the roots. So now I'm going to calculate okay, so my roots go like this. So this equation gives me whereas my other equation, it should be s squared plus 2 alpha s plus omega naught squared equal to 0. So what I'm doing here is that I'm comparing, right? I'm comparing two equations. If I compare these two equations here, what do I end up getting? Well, what it tells me here, it tells me what here? It tells me that right away, if I look at this, you can see that omega naught squared has to equal to 1, so therefore omega has to give me 1. The question is, what about the second term? The second term here tells me that 2 alpha is equal to 1/2. So then I get 2 alpha equals 1/2. So this tells me here that alpha must equal 1/4. So looking at this combination, omega naught must be bigger than alpha. So if omega naught is bigger than alpha, this means that it's underdamped. And without even thinking about it, my solution for the current of the inductor now has to be what? It has to be A1 e to, it's e to the minus alpha t times A1 cosine omega t plus A2 sine omega dt. Okay, so what's alpha in my solution? Well, alpha is equal to 1/4. What is omega d? Omega d, from what we talked about earlier, is sort of the term that reads what? Omega naught squared minus alpha. So I got to get those two things here. So this guy, if I plug this guy in here, what I'm going to get here is that I'm going to get what? 1 squared minus 1/4 square root. So this is not a pretty number. So when you calculate this number, I get 0.968. And these are all, this is in rads per second. So now I got omega d, so what's my solution look like? Well, it should be IL of t. By the way, I didn't get my b value. But for right now, let's look at this thing. So this will be e to the minus t over 4 times the quantity a e s1t. Oops, nope. Keep messing up. A1 cosine of 0.968t plus A2 sine of 0.968t. So that's my solution plus my b. So one thing that I forgot to do here is I should have calculated my b constant right away. So the question is, what is b? Go to the circuit. Look at the circuit here. Look at the current of the inductor. As t goes to infinity, what's the current of the inductor? 0. So by inspection, IL at infinity has to be 0 since cap open. Okay, so we know it's got to be 0. Does our equation tell us that? So So what we do here is that we assume IS, the source current, is a constant. Why is it a constant? Because I'm going to give you a constant. That's why. All sources are constant. So now, look at the equation. So if I look at my equation, it's s hat squared plus 1/2 s plus 1 operating on the function like this, which is then equal to 1/2 s hat is. So what does this equation tell me? It tells me this, that if IL is equal to B, which is a constant, and I plug that right into this equation here, I'm going to get what? I'm going to get s hat squared B plus 1/2 s hat B. And since these guys are derivatives, that immediately goes to 0. Right? Because they're derivatives. So then I get what? Plus B, and then this equals 1/2 s hat of a constant source. So then this guy also goes to 0. So if that's 0, that's 0, that's 0, B has to be 0. So this implies here that B is 0. So when I look at my solution, you can see that this term has to be 0, and so therefore I have this. This is my current right there. So what does that mean? Well, it means this. That I'm going to have some oscillation. And my oscillation is going to be underdamped. And when I calculate the period, let's say I calculate the period from here to here, that period d is equal to 2 pi omega d. What's omega d? That right there. And by the way, you will do this in the lab and measure that. Okay, let's go to the next circuit. We're going to do so hot there for 10 minutes. Okay, let's go to the next one. The next one is which one? Yes.
I think, is it alpha minus lambda or minus omega? Omega minus alpha.
It's omega minus alpha. Okay, well, yeah, because that's how you get the complex roots. So let me make sure I get the right circuit. Okay, here's the next circuit. So now we got what? Example 9.3, what did I call it? B? It's the second circuit. So here I have what are we solving for in this circuit? Is it the current? Yes, the current. So in this circuit here, we're solving for IL. So what's the values that they give us here? This is 4, 6, 1, and then this is a quarter of farad. Let's do this. Okay, ready? Here we go. So if I do this, I'm going to look at KCL, and I'm going to look at KVL. What am I solving for? This guy. So when I go to look for my second equation, it's got to be the derivative of that guy. Note, earlier I was looking at variable 2, but IL was variable 1 as far as our notation is concerned, because I want you to just look at it. So let's do it. So what I'm seeing here, I got to look at all of these currents here, right? The KCL has only really one node all the way across this thing. So that means I got to do what? So 5 amps must equal the current of the 4 ohm plus the current of the inductor plus the current of the capacitor. Right? At the top node, that 5 amps is going like this. What do I got to change here? Look at that 4. I got to change the 4. Look at the IC. I gotta change the IC. Let's go do it. Then this tells me here that I gotta change this. How do I change this? Look at I4. Since they're all parallel, it must be parallel to what? The voltage of the capacitor. So then I go 1/4 VC plus IL. I look at this guy, I gotta convert it into an operator. So then this means here it's gotta be plus the capacitance times S hat VC. So when I look at this guy here, you can see automatically that right now I have everything in terms of VC and IL. I'm looking good. But I'm not looking good, but this is good, right? So now if I look at KVL, I got to relate the voltage of the cap and the voltage of the inductor. Note that these two are in parallel. So that means that cap voltage must equal the sum of these two. So then I'm going to say VC must equal the voltage of the 6 ohm plus the voltage of the inductor. So when you see here, I have what? Voltage for the 6 ohm resistor, which I got to change, and I see VL, which I got to change. So what do I know about V6? It's in series with the inductor. So that means then I could come in here and write this as 6IL. Okay. How do I convert that? It's got to be its inductance times S hat IL. So then this will be S hat IL, and that has to equal VC. Here's my second equation here. So what am I solving for? The inductor current. I need the derivative of the inductor. Where's the derivative of the inductor? Not here, right there. You can see that that's my equation 2. So now let's matrix this guy up. Okay? Let's look at the matrix. So I'm going to clean this up here a little bit. Let's see if we can do this a little bit faster. See this guy here? VC? See that quarter? I'm going to get rid of that quarter. Because I want easy things when I take the matrix. So I'm going to multiply everything by 4. That becomes 4. That becomes 20. Okay? Here I go. So I'm going to write 1 plus VC, 1 plus S hat VC, right? And then I'm going to get 4IL, and then I'm going to get 5 times 4 gives me 20. That's my first equation. Look at my second equation. See that VC? I'm going to bring it to the other side, so I'm going to get a negative sign. So when I do that, I'm going to get minus VC plus 6 plus S hat IL equals 0. Now I'm going to make my matrix now. If I make my matrix, it's going to be 1 plus S hat minus 1, 4, 6 plus S hat. Look at IL now. It's the second variable, not the first variable. So how am I switching? It's just convenience. What do I think is convenient? Could you have done it the other way? Absolutely. Remember, you figured out what works for you. Here I go. So note, I'm going to start taking a little bit of shortcuts now. We know that this guy is D. And so what I'm going to do here is that I'm going to calculate D right now. Okay? So if I want the solution, it's got to be dx2. Right? That's what I'm looking at. So here I go. So in this case, it's not x2, it's going to be IL times this determinant here. Okay? I'm going to do it right in one step. So then I multiply these two together, and then I subtract these two together. So if I multiply these two together, I'm going to get 1 plus S hat, 6 plus S hat. And then I do this, so this is going to give me minus minus, which gives me plus 4. It's operating on IL, and then I change in my matrix. Since I'm looking for IL, note that it's in the second position. I'm going to take these guys and I'm going to put it in that column right there. So then it's got to be 1 plus S hat minus 1, 20, 0. See? So I'm trying to save some time here. Now I gotta multiply out this mess here. Let's see if I did anything right. So here. 1 times 6 gives me 6. And look at that 4. Plus 4 gives me 10. Now remember, don't let me cheat, right? Don't let me get away with simple mistakes here. Now I'm going to go after the s hat term. So the first one gives me 1 times s, gives me s hat. And then 6 times s hat gives me 6s hat. So I get 1 plus 6 should give me 7s hat. And then the next one here has to be the s hat square term. And you can see that's going to be s hat plus s hat gives me s hat squared. That gives me IL. And then this gives me, now I'm going to do this here. 1 plus s hat times 0 is 0. And I get minus 20 gives me 20. There's my equation right there. So what am I going to do? I'm going to go after the roots now. Let's see. Did that work out for me? What do I get? I don't know what I got. I can't see right now. Is that right?
Yeah.
Is that, okay, good. You know, I'm making up all this shit, by the way. Right? Yeah, I remember my son asking some years ago when he was about 7, he said, is that a language that you're studying, Dad? Yeah, it is, right? How many people can speak mathematics? Not that many. Okay, let's go after the roots now. So, next we want to determine the roots. So the roots here, wait, we gotta go get the B constant. We gotta do the B constant first. Look at the circuit. Look at that guy right there. The current of the inductor. What is the current of the inductor at t equal to infinity? Okay, I'm going to do it right here, okay? So now I'm coming this direction. Why? I got space right there. So if I look at this guy here, it tells me that at t equal to infinity, I'm going to get 5 amps. And then I'm going to get a 4 ohm resistor. And then I get a short here. And then I get an open. So what I'm seeing here is that I have a 4 and a 6 right here, but now the inductor current is going where? Right there at t equal to infinity. So what I'm seeing here is that the current of the inductor at infinity must be the current of the 6 ohm resistor at infinity. So clearly there's nothing here, so what am I going to use? I got to use current divider rule to get that current. So here we go. So the current of this guy has to be what? The opposite current divided by the sum. So I get the opposite resistance. Look at that, I said current, right? But we're among friends. So we know that my language is all, well, I shouldn't say that, okay? But it's got to be the sum of these guys here times the source current. So look at that. I get 4 divided by 10 times 5. These two cancel out. I get a 2 in the bottom. So therefore it should be 2 amps. So B better be 2 amps. Okay? Look at the circuit. If I put in IL as B, I get the second derivative of B, which is 0. I get the first derivative of B, which is 0, so that in the end, I'm left with this equation right here. So I get 0 plus 0 plus 10b equals 20, and look at this. Dude, this is sweet, right? So that looks good so far. So I got my B constant. So what's the force response for the circuit? It goes to 2 amps. Okay? So when I look at my solution here, that means my total solution, my B here has to be 2 amps. So now I want to go determine characteristic roots. So what do I get here? So if I look at that equation here, the roots have to be what? I get S squared plus, I don't even know where I'm looking on this thing. Right? Is that the equation? From there. Can I break this up? Sure we can. That's what I mean by being nice. You look at that, this implies here that S1 is equal to -5, S2 has to equal -2 in order to satisfy that equation. So if I do that, these are real and distinct. This has to be what? Over damped. Now I could have done it a different way, okay? But you gotta admit, that's the fastest way. But the other way here, I compare this to this guy right here. And if I did it this way, what you're seeing here is that I would pick what? So I know that 2 alpha has to equal 7, and I know omega squared has to equal 10. So what I'm seeing here is that alpha is equal to 3.5, omega naught squared, or the square root of omega, is that. And that has to be less than that, right? Because this has to be just a tiny bit above 3, which tells me that alpha is squared into omega naught, which then tells me it's overdamped. Okay, and then you would go back and you would go into that equation, and then you would start doing this here. You would do 3.5 plus or minus 3.5 squared. Oops, I got to do the other one. Times, yeah, it is. It's 3.5 squared minus 10. And then you would get those roots. And when you calculate those roots, you would get 5 and 2. But since I'm your friend, I try to make them easy when I can. And that's what I mean by that. So then, what do I mean? That means that the solution must be what? So I go, IL of t has to equal A1 e to the minus 5t plus A2 e to the minus 2t plus the constant 2. That's my solution right there. Yes? Any questions? Let's go to the next one. So now we're at example 9.2 or 9.3C.
Already we go.
So I got a switch here. Okay, so it's 20 volts plus or minus. That's so this guy here is quarter F. This guy there's another resistor. This is 1 ohm, and then this is a 10 ohm. And we know switch opens at T equals 0. So let's think about this physically before we do anything. The thing that's close, what's it gonna do? It's gonna short this guy here. So then that means I only have one loop, because that short's gonna kill everything off right here. So if I now open this switch, what happens? There's no more sources. If there's no more sources, that means my force response has to be 0, since there are no sources. So when I derive my equation, the right side, the effective source term, has to be 0. It has to be 0, no choice. So if I don't get that, I made a mistake. Let's do this thing. So what does the circuit do here? So after switch is thrown, then we have what? We have the inductor, we have the capacitor, and we have the resistor. So I have 1 ohm, I have a quarter F, and I have a 2 Henry. Tell me, what are the directions of the current? It has to be down. Wouldn't you agree that this is the node here? Wouldn't you agree that this has to be the ground? And this node right here has to have some voltage, there's only one. So which direction does the current going? Down, down, down. So where my current's going? Down, down, down. You try to do something different, you're going to get the wrong answer. So now, let's go do it. So I'm calculating, what am I calculating? The capacitor. So let's go do that. So, here we go. So I'm going to do KCL. What does KCL tell me? KCL tells me that these 3 are all pointed towards the ground. So it has to be IL plus IC plus I11. So you can see I have 2 terms, right? I got to convert the IC to VC. I got to convert that to IC or VC. So then what am I going to do? That has to equal to 0. Now this tells me that IL is good. This guy, I got to convert. So that's a 1/2, so it's got to be 1/2 S hat VC. Let's go to the next term. This is a 1. Note that these 2 are in parallel. So then that means here that this has to be 1/1 VC equals to 0.
Wait, Skylight?
Yeah.
I think it's 1/4. I think you changed
We just copied it.
Okay. If you want to worry about details, I just right? I can make those mistakes. You cannot, of course. And then I point my finger at you, going like, shame on you, how you could do that. Let's go to KVL. KVL tells me what? Well, these 2 are in parallel. So then I'm going to write VC must equal VL. So what am I going to do? I'm going to bring that to the other side. So then this tells me here that it's got to be VC, but I got to convert VL. VL, when I look at that, it's 2 Henry. So it's got to be minus 2 S hat IL equals to 0. So since I'm solving for the capacitor, what is the derivative term of the capacitor? That guy right there. So this is the guy that we would be calling in that old notation as 2. This is the one that's going to help us in the next step. So let's go do this. So I'm going to matrix it up. So now I'm going to skip a step. What I'm going to do here is that I'm going to just automatically put it into matrix form. So here we go. These 2 are combined here. So this means I'm going to write 1 plus 1/4 S hat. And then my IL term is going to be 1. No, I'm already setting it up, so this is the way I did it here. that I'm doing this here. And then what's my source term? 0. That's good. We want a 0. Now let's look at the second equation. Since I wrote VC first, I'm going to write this as 1. The second term here is minus 2 S hat. What's my source term? 0. Beautiful. If I get these C's to be 0, that means that the differential equation has to equal 0. So here we go. So now I'm going to cross multiply, right? Positive, negative. So this guy gives me a negative, so I'm going to get minus 1 plus a quarter S hat. There's a 2 here, so I'm going to put minus 2. So that minus 2, I'll put it on in front. And then I get this cross term, which is also negative, so I get 1. So these guys now operate on VC, and you can see that when I do the right side, I'm going to get 1, I'm going to get 0, 0, 1, minus 2 S hat, and you can see that I'm just multiplying everything by 0, so it's got to be 0. And that's a good sign. So see that minus sign, I'm going to get rid of them. So if I do that, I'm going to get the following thing. I'm going to get, so the first term here, I'm going to get 2S hat plus 3. Is that right? Right? That gives me, no, plus 1. And then I need the S squared term, so that 2 gives me a 1/2, so I should get 1/2 S hat squared plus this. Now let's see, let me check my algebra here. Is that right? I think so. Yes, that's correct. Okay, so then here's my equation. So now that I have my equation, I then got to go do what? Determine the roots. So let's go determine the roots. So when I look at this roots here, let's do it the other way just to be careful here. The other way that we could do it here is that we can compare this to what? S squared plus 2 alpha S plus omega naught squared equals to 0. So what do? I'm going to calculate alpha using this. So if I just compare these two, you see that I get 2 alpha equal to 4, and I get omega naught equal to 2. Right? Is that? Let me see what I got. My solutions tell me I have a mistake. Where's my algebraic mistake here?
It's 4 pieces. No, down. There are this 4 is not 2.
So that's 2, and then that's 1/2.
Then you multiply everything by 1.
Carlos,
Yes,
should it be -3, not +1?
this one?
No, you can use -2 times 1, -2, minus 1.
But remember, I took off the minus sign. I had an error. Let's go look at this here one more time. Right? This has to be true. So I get a quarter VC, that looks good. This guy, 2, that looks good. So when I come over here, it's got to be VC plus a quarter S hat. Okay? This guy looks like 1 minus 2 S hat. I think that looks good. Let's do the multiplication now. So if I multiply these two, I'm going to take that minus 2, put it right there. I get 1 plus 4S times S. That looks good. And then I get the minus 1. Okay? So if I multiply this out, I'm going to get 2. That's my term right there. My second term is 2 times a quarter. Gives me a half. square. That should be cool right there. But yet, I'm getting this relationship right here. I wanted to do a critical. And I'm showing that I don't have critical. Well, maybe we could pretend for a little bit. Where did I mess up on my... I keep telling me that I get a 2 here. Yeah, so I think that's not what I wanted. That's not what I wanted.
Which part?
So if I look at this guy here, you can see that in this case, I'm going to get that alpha squared into omega naught, which means that it's over there.
Is alpha is 2.
Right? And I'm going to say, I'm not going to go any further.
Look at the matrix.
I wanted to do critically down, but my solution tells me it's over.
This would just be -2x.
Say it again.
Just
1
always
minus
that one.
minus 1. Flip it over to the negative.
If I make that resistor 1/2, well, I'm not going to come to it. So, dude, what happened to the 10 minutes per problem thing? And we still got step 3 and 4. Isn't that sweet? We got a busy Wednesday. Okay, I will see you on Wednesday.